Okay, this video is for the 7.5 lesson in my grade 11 applied math course. And this one's not in our notes package. We jumped from 7.4 to 7.6 because we used to leave this part of the chapter out, and we aren't supposed to leave it out anymore. So we're going to go back and start by just remembering how our algebra skills worked in grade 10. If I had to expand or simplify, both of those directions mean the same thing, something like 2 times 3x minus 5, where the 3x minus 5 is in a bracket, remember that you are supposed to multiply the 2 by both things that are in the bracket, right? We call that the distributive property of algebra. I don't care if you don't remember the distributive property of algebra, but you have to know how to do it. 2 times 3x is 6x. 2 times negative 5 is negative 10. So this simplifies to this. This is a simpler answer. It doesn't have brackets in it. Okay? And then suppose I wanted to simplify negative 3x times, open a bracket, 2x minus 1. Same trick. I multiply negative 3x by both things in the brackets. I distribute it. So negative 3x times 2x is negative 6x squared. And negative 3x times negative 1 is positive 3x. Don't forget that a negative times a negative makes a positive. So that allowed you to do things more complicated, like this question down here. All right, how would I do that? Well, before I simplify, before I try collecting any like terms, I have to get rid of the brackets. So again, 2x times both of those things and negative 3x times both of these things is going to give me 8x squared minus 6x minus 6x squared plus 3x. And then I know that these two things here are like terms, so I add them together. 8 minus 6 is 2. And I know that these two things are like terms, so I collect them. Negative 6 plus 3 is negative 3. This whole thing is equal to that thing. But this is simplified. All right, that's expanding. Factoring is in fact the exact opposite of that. One last type of expanding before we review factoring. What happens if you multiply a binomial times a binomial? We did this for a few minutes at the very beginning of this chapter, but let's put it into our notes now. Remember that you have to now go x times x and x times negative 5, and then you have to go negative 3 times x and negative 3 times negative 5. So you have 4 multiplies to do. And if you do that, you're going to get the first times the first, which is x squared, the first thing times the last thing, which is minus 5x, and then this little arrow here would be negative 3 times x, and then this bottom bigger arrow is negative 3 times negative 5. And the like terms that you can collect are these two. And you can say negative 5 minus 3x is minus 8x plus 15. Interesting. You started with 2 binomials, you end up with a trinomial, and that should start looking familiar. You should be going, oh yeah, these are the kinds of things we've been working on in Chapter 7. So, multiply this out now. This one's a little harder because the x's have coefficients in front of them, but the logic still is the same. My favorite part about math. The rules don't change because the numbers get more complicated. 2x's times 3x's is 6x squareds. 2x's times 4 is 8x. Negative 3 times 3x is negative 9x. And negative 3 times 4 is negative 12. Collect those two like terms, and I get 6x squared minus x minus 12. Okay, now all the skills we just did, we should be able to do backwards. What if we started with one of these things, or the stuff previous, and said we wanted to go backwards and go back to what their factors were before they were simplified? That's what's called factoring. So when I look at something like x squared minus 2x, I go, okay, I can factor an x out of both of these things. And now it's in factored form again. Look at this example. I can factor 3x out of both those things, giving me 2x minus 1. Remember that once you're factored, you should be able to multiply the two things together and get the thing you started with again, if you wanted to. Now, in grade 10, that was as far as factoring went. I think I made this point earlier in the chapter. It's like we taught you how to do this skill, and we didn't really show you what it was useful for. Well, now here in grade 11, we want to be able to solve equations that have x squareds in them. And notice that the two things I just did are the skills that would help me solve these two equations. If I look at this equation and go, how much is x? I can factor like so, and then I can say a number times a number is 0. That's possible to solve if the first number is 0 or the second number is 0. And if this factor here is 0, then the number that makes it 0 must be 2. So this equation has two solutions. X is 0, x is 2. And this relates to what we've already been doing this unit in that, recall, you don't have to write this part down if you don't want to, but recall that if this was y equals x squared minus 2x, and I were to graph it, oop, I thought I was typing and I was not. There we go. Notice it has two x-intercepts at 0 and 2, which are the same things we get when we solve that equation, right? That equation, if you set y to 0, remember your x-intercepts happen when y is 0. So that's how the geometry and the graphing relates to the algebra. Okay, this one here is basically the same as this example here. I would move the 3x over to this side. Oops, let's go back to black. Move the 3x by subtraction to this side, leaving nothing but 0 on that side. I can factor out 3x, leaving behind 2x minus 1. And then what makes this thing a 0? Well, if 3x equals 0, x must be 3. It's 3. Must be 0 divided by 3, which is still 0, right? 0 divided by anything except 0 is always 0. And this one's a little harder. What if 2x minus 1 is 0? Okay, well, then I'd add 1 to both sides. I divide both sides by 2, and I get a half. So again, using my Desmos, if y had equaled 6x squared minus 3x, I should get x-intercepts at 0 and a half. Let's see if that's true. So 6x squared minus 3x. Yep, I'm going to have to zoom in a little perhaps, but my x-intercepts are 0 and a half. Yep, it works. Now, I'm going to do this in red. Remember, when I grab the red pen, I'm making a mistake on purpose. Some people are going to look at what I did here and go, man, there was a simpler way to solve this question. If I was looking at this, why don't I just divide both sides of the equation by x? And then those x's cancel, and 6x equals 3, x equals 3 divided by 6, x equals 1/2, and oh, wait a minute, what do you notice? I only got one of the solutions. There's two solutions. How come I didn't get this one? How come I didn't get that one? What's the unbreakable rule that you're never allowed to do in math? You're never allowed to divide by 0. And this is one of the reasons why. Notice that when I divided both sides of the equation by x, if x was 0, you're not allowed to do that. And because you're not allowed to do that, you didn't get both of the solutions. You only got one of them. So avoid thinking this way. Think factoring. Whenever you're going to solve an equation with an x squared, move everything to one side, leave 0 on the other, and try to factor. I have a question from the back. Yo. Okay, excellent question. If you always have this side being 0, won't the x-intercepts always be 0? Yes, when the equations look like this, where it's an x squared and an x squared and an x. But what happens when I have another constant besides the x squared and the x? Now x is 0 is not going to be my solution. In fact, now I have to do the opposite of what we did back here. The opposite of that expanding. You're going to say to yourself, you're going to say, self, what two binomials multiplied to make this trinomial? Now you know that x times x is what gives you x squared. That's pretty much a guarantee. That's an easy part. But how do I know what goes here and here? Well, I know those two things multiply to make 12, but there's lots of things that multiply to make 12. There's 1 times 12, there's 2 times 6, there's 3 times 4. Which pair do I want? That's right. We want the 3 and the 4. How come? Because they add up to 7. Remember that from grade 10 factoring? Is MAP coming back to you? All the happy MAP memories coming back to you? That's good. So plus 3 and plus 4. And of course, you now, of course, have to solve that. So x plus 3 is equal to 0, or x plus 4 is equal to 0, which means x is negative 3, or x is negative 4. Notice neither of those is 0, which makes sense. If I, again, graphed, let me get rid of this guy, y equals x squared plus 7x plus 12, I get two answers for the x-intercepts, negative 4 and negative 3, which is the same thing I just got here. Right? And you can check this, right? If you're not sure if you factored right, multiply it back out again. You should get your original check, your original question. X times x is x squared plus 4x plus 3x plus 12, and yeah, that's going to add, that's going to work. All right, let's do more of these. X squared plus 13x plus 12. Now, once again, I know it's going to be x and x. And I know that whatever goes here times whatever goes there is 12, but it obviously can't be 3 and 4, because 3 plus 4 doesn't add to make 13. What two numbers times to make 12 that do add to make 13? 12 and 1. So plus 12 plus 1. So x equals negative 12, x equals negative 1. I seem to like the number 12 today. We got all kinds of examples with the 12. Look at that one. X squared minus 8x plus 12. Let's think about that one for a sec. I have one more question. Yep. Where did the negative come from? Remember that. Okay, I kind of skipped a step that I did in the last one. I'll refuse to skip that step on this one again. Why did the answers end up negative when these are both plus? Because remember what's happening here. We're solving an equation where something times something else equals 0. The only way you can multiply two things and get a 0 is if one or both of them is 0. So what if the yellow one was 0? Then x plus 12 would equal 0. So solve that for x. X would equal negative 12. What if x plus 1 equaled to 0? Then x would equal to negative 1. So yeah, your solutions tend to always be the opposite of your factors. But before you all go memorizing that as a rule, it gets a little weirder than that. You'll see in a minute. Okay, we got two more examples with 12s because we just love the number 12 today. This one's weird though. Okay, x and x again, right? But wait a minute. The two numbers here multiply to make a plus 12, but they add up to make a negative 8. How is it possible that two numbers add to make a negative, but they multiply to make a positive? What do I know about those two numbers? They both have to be negatives, right? Somebody figured that out. They both have to be negatives. Does the logic of that make sense to you? Now, what two numbers times to make 12 where they're both negative, but if you add them up, you get negative 8? It's negative 6 and negative 2. Now my answers for x will be positive because x minus 6 equals 0 is one of the factors' answers, and x minus 2 equals 0 is the other. So x would be 6 or x would be 2. I'll give you a sec to catch up to me. I know I'm writing fast. Sorry about that. I want to give you guys lots of time to work. So once again, and you don't have to write this part down if you don't want to, but how this relates to the other stuff we've been doing throughout the course here, throughout this unit, is if this had been y equals x squared minus 8x plus 12, it would have x-intercepts at positive 6 and positive 2. And again, we can show you that. So y equals, so negative 8x instead of plus 7x. Watch the x-intercepts move to positive 2 and positive 6. And again, we could find this vertex. What's halfway between 2 and 6? 4, which is why that's a 4, right? And then once we know that this number has to be a 4, we can run 4 through here. 4 squared is 16. 16 minus 32 is negative 16. Negative 16 plus 12 is negative 4. And of course, we know that the y-intercept is going to be 12. There it is, because if x was 0, y would be 12. Notice how all this stuff relates. The graph, the algebra. If you think of geometry and algebra and arithmetic as 3 different subjects, stop. They're all one thing. So anyway, one more with the 12s. This one's different. This time the 12's a negative. If you multiply, oops, I want to go back to black. No. If you multiply together two numbers and you get a negative, what do you know about their signs? They're opposites. One of them has to be a plus and one has to be a minus. So now, ask yourself what two numbers times to make negative 12, but when you add them, you get a negative 1. It's going to be negative 4 and plus 3. And it matters which one's the minus. The 4 has to be the negative or else you wouldn't get a minus 1. So the two answers for this one are x plus 3 is 0 and x minus 4 is 0. So x is negative 3 or x is 4 are the two solutions to that equation. Okay, I'd love to tell you that that's as easy as factoring ever is, but of course, like everything in math, it gets more complicated than that. So let's look at a couple of special factorings. Like, what about that one? Now you're probably looking at that going, well, that's different than the ones we just did because that's not a trinomial. Well, it kind of is. If you like, you can think of this as x squared plus 0x's minus 4. Get it? Because 0 times x would be 0. Ah. So now ask yourself, say self, what two numbers times to make negative 4, but they'd add to make nothing? Well, the only way to add two numbers and get nothing is if they're exactly opposite, right? And the only way to get a negative when you multiply is if they're opposites. What two numbers times to make negative 4 but would add to make nothing? Plus 2 and minus 2. We call this, in fact, this has a special name. We call this a difference, I don't care if you remember this name or not, of squares. Good, you remember that from grade 10? And these two things have a special name too. These two things are called conjugate pairs. And I love that that rhymes. Difference of squares makes conjugate pairs. Kind of a Dr. Seuss feel to that. Conjugate pairs, difference of squares. I will not eat them, Sam, I am. Question? They both have to be perfect squares, yes. Notice it says difference of squares, not difference of a square and not a square. It's got to be two things that are perfect squares, like the next one. I love how both of the questions you've asked have exactly led to my next example. Should put you on the payroll. Notice the next one, I actually already have that one done for you. 9x squared minus 49. Those are both perfect squares. So it's 3x plus 7, 3x minus 7. I'll give you a sec to catch up to me. And then we're going to go back one more time to the opposite of factoring again. Let's remember how to multiply something by itself. Let's expand. Okay, everybody got up? We good? Can we move? Okay. I'm picking up the red pen. What does that mean? It means don't write this. He's making a mistake on purpose. I want to square this bracket. Fine. I'll square the x, and I'll square the negative 5. If I square x, I get x squared. If I square negative 5, I get plus 25. That's not right. I can prove to you it's not right. If it was right, any number I put in for x, this side should be the same as that side. Let's say my favorite number was 4. 4 minus 5 is negative 1. Negative 1 squared would be 1. 4 squared is 16 plus 25 is 41. Does 1 equal 41? Not last time I checked. Something's gone wrong. Some of you are shaking your heads. Yes, I remember my grade 10 teacher making a really huge deal of this. What should you do with x minus 5 squared? Let me get rid of all this nonsense. It's wrong. What should you do with x minus 5 squared? You should think of it as x minus 5 times itself, the entire factor. It's the same stuff we were doing a few minutes ago. It's, if you like calling it foiling, first outside, inside, last. X times x is x squared. X times negative 5 is negative 5x. Negative 5 times x is negative 5x. And negative 5 times negative 5 is plus 25. Notice these two things don't go away. Negative 5 minus 5 more is negative 10x. That's how it expands. In fact, you kind of get to the point where you get very good at this once you did this. Probably some of you in grade 10 probably memorized this. When you see a binomial times itself, which squared, you just square the first thing. That's this guy. You square the last thing. And you notice that this thing here is the two things times together and doubled. 5 times 2, or sorry, 5 times x times 2. That's where you get 10 from. Once you made that recognition, and you start calling this a perfect square trinomial, you start recognizing that you can factor one like this really easily. This is a perfect square. This is a perfect square. If I square root the two things, this would be x and this would be 4. 4 times x doubled is 8x. So you go, oh yeah, that's going to be x plus 4 all squared. And so now when we're solving an equation and we're using our factoring skills, jot that one down. Let's solve that one. We're going to say this is x plus 3 squared equals 0. And how do I know that's x plus 3 squared? Because 9's a perfect square, its square root is 3, and 3 doubled is 6. If you don't believe it, you can multiply it out. You can do a check if you want to. You don't have to write this down if you don't want to. Right? X squared plus 3x plus 3x plus 9. Yep, it makes this thing. And that now is very easy algebra to solve, because now I can just use my opposite operational algebra technique. Square root both sides. It gets rid of the square. What's the square root of 0? Yeah, still 0. And then minus 3 from both sides of the equation. And notice, we just talked about this a few minutes ago. This wasn't on the video. This was us going over old homework. Sometimes parabolas only have one x-intercept, and it's a case just like this. If I was to graph y equals plus 6x plus 9, go away keyboard, Notice that the vertex is right on the x-axis, so it only has one x-intercept. And how does the algebra reflect that it only has one x-intercept? It only has one solution when you solve it, because it's a perfect square trinomial. Isn't that cool? Let's try another one. Or let's try a bunch. Here we go. I'm going to pause the video so that my guys in class can try these 4 questions, and then we'll come back and we'll see if we can solve them together. Okay? So everybody at home who's watching this on video, give these a try, and we'll be back in a minute. Okay, we're back. So, what 2 numbers times to make 6, but add to make -5? It'd be plus 6 and, oh, sorry, my bad. Minus 6 and plus 1. I was thinking ahead to the answer. The answer then is 6 and -1. Okay, what 2 numbers times to make 56 negative, but add to make -1? Well, again, if they multiply to make a negative, they must be opposites, plus and minus. And what 2 numbers times to make 56, but they're only apart by 1? Yeah, the most commonly forgotten numbers in your times table. Did you know that? Well, except for the 12s. People don't remember the 12s very good. But from 0 times 0 up to 11 times 11, the most commonly forgotten times table fact is what's 7 times 8. So yeah. And which one has to be the plus? The 7 has to be the plus, correct. So x is -7, x is 8. This is my perfect square trinomial. What 2 numbers times to make 4 and add to make 4? They're both 2's, but they both have to be negatives. So x equals 2. And finally, what 2 numbers times to make -4 and add to make -3? So -4 and +1. So x is 4 and x is -1 are the solutions. So there we go. One step harder than this. Maybe somebody's already noticed what I've done to make all of these pretty easy. Notice none of these questions have a number in front of x squared and a number different than 1. What happens when that number is not a 1? Well, then it gets a little harder, but that doesn't mean factoring doesn't work. First of all, sometimes you get lucky, and that a number that isn't 1 is a factor of all 3 terms. So I can just divide the entire equation by 2. So x squared minus x minus 12, and 0 divided by 2 is still 0. Haha, there we go. Tried to make this work harder. 2 didn't work. We've seen this one already. This one's -4 and +3. So x equals 4 and x equals -3. Sadly, sometimes the a value that isn't 1 doesn't just nicely factor out of all 3 of them. Like, look at this guy. I can't factor a 6 out of here. That would make this 1/6. I do not wish to play with fractions. Thank you very much. What do we do here? Well, I'm going to maybe do a quick example down here before I get to that example. Do you remember foiling when these numbers here weren't 1s? 3x times 1x is 3x squared. 3x times 2 is 6x. -4 times x is -4x. And -4 times 2 is -8. Getting low on time here. So this is 3x squared plus 2x minus 8. So now if I was going backwards and I was trying to solve for x in that equation, I'd go, what 2 numbers times to make -24 but add to make 2? And oh yeah, that's 6 and -4. So I decompose. This is called the decomposition method. And then I factor out a 3, and I factor out a -4, and then I factor out an x plus 2. And then x plus 2 is equal to 0, or 3x minus 4 is equal to 0. So x equals negative 2, or 3x equals 4, so x equals 4/3. There's the two solutions to that one. I'm going to leave you with this last example. If you now try the last example I just did with that method, we'll pick it up right there tomorrow, see if you can solve that. All right? And that's where we'll leave it for today.